I guess we are going to start this afternoon session. So 2 remarks about this morning lectures. First one is that I forgot a 2, and people noticed it and didn't tell me, which is nice. But the -1 to the p of gamma times the thing, when I bounded by 1 minus the thing, it was 1 minus twice the thing, right? That's exactly, I was feeling weird, like there is a 2 missing, but I thought that, I just forgot it. Okay. Second comment, which was, this time it's not a mistake, but maybe it was not so clear from the explanation. It's not like there are so many things to do in Saint-Flour or than, Okay. No, it's that if you want to get -1 and that you already have 1, you need to do -2 something. That was really a silly mistake. Yeah. Okay, so second comment, which is not a mistake, but I think like somebody told me that he had some trouble to find the solution. So it was in this P1 plus, P1 plus sum for C in A1 of C equal P2 plus sum in C not in A1 of C, C let's say in A minus A1. Why this thing is intersecting an even number of time P2, E2. Clearly, every cycle intersects an even number of times the union of E1 and E2. Intersects E an even number of times. But E2 is just a part of it. But by definition, these cycles, because they are not in A1, they do not intersect E1, so the number of intersections with E is the same as the number of intersections with E2. Okay? That's, I should maybe have said it more clearly. I should have said it probably. So that's why here you have an even number of intersections, here an odd. Therefore, this thing has to intersect. This doesn't, so this is necessarily one of these cycles. Okay. Last comment, solution to the problem. Why are there just exponentially many connected sets in a graph of bounded degree D, connected sets containing the origin, of length k, of size k, okay? And the idea is the following. Just take Bernoulli percolation. Okay, so Bernoulli percolation is just percolation where, it's just, okay, maybe I should do it. So Bernoulli percolation. So every edge of your graph is open with probability P and closed with probability 1 minus P. So you obtain a graph, okay, which is a subgraph of your original graph with the same set of vertices and a subset of edges, which is just made of the open edges, okay? Now look at the probability that the connected component of 0 in this graph has cardinality k. Right? This obviously is smaller or equal to 1. It's a probability of something. Right? But this is also the sum over every connected set of cardinality k containing the origin. So sum for every C connected set, blah, 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 of the probabilities that the connected component of the origin is exactly this guy. And in order for the connected component of the origin to be exactly this, well, you need a certain number of edges to be open, a certain number of edges to be closed, but for sure, all these edges must be incident to one of the vertices of C. So at worst, the probabilities that a certain set is the connected component of the origin is the mean of P and 1 minus P to the number of edges incident to the guy. So at worst, this is going to be D, if D is the degree of your graph, times the cardinality of your guy, which is K. Okay? Take P equal 1/2, and you obtain automatically that the number of ways, number of such C's, times 1/2 to the dk is smaller or equal to 1, so the number of guys is smaller or equal to 2 to the d times k. So, I mean, I do think this is due to Kesten, but this is the types of very simple arguments which can actually trace back much before because they are often rediscovered by people. Of course, this doesn't give you the right, I mean, 2 to the d is not the right rate of growth. You can do much better than that. For instance, Bolobash has a much more precise bound in his famous book where he gets, I don't remember exactly what, but I mean, something better than that. Okay, but for us, this gives us an exponential bound, which is sufficient to run the end of the argument and to conclude the proof. Okay, so you will see tomorrow, or actually even this afternoon, no, actually now, yeah, you will see that it's not really, I mean, this pairs argument in dimension 3 and more is, I mean, I wanted to show it to you because I think that there are two very cute arguments here, just for elegance of math, but it's not the simplest way of deducing that beta c is smaller than infinity. What we are going to see, if you do the same for Bernoulli percolation, for instance, for people who already did a class on Bernoulli percolation, what you usually do is in dimension 2, you prove it using duality, and then in higher dimension, you just said that the PC is smaller than the PC in dimension 2. The bigger the graph, the smaller the PC. And here it's the same. The bigger the graph, the smaller the beta c. And this, if you can prove that this credo is true, then doing it in dimension 2 was sufficient to actually imply that in ZD, beta c is smaller than infinity. So this was just for just a detour to show you these arguments. Okay, so lecture 2 now. We are going to discuss the high temperature expansion of the Ising model. So it's another graphical representation. The goal is, again, to try to rewrite quantities in the Ising model in terms of, in terms of graphs. But this time it's going to be more convoluted. There are not going to be any bijection between sigma and the configuration that we consider. Okay, so maybe first thing, the high temperature expansion itself. So in order to do it, sorry, I will need a notation. So for a subgraph omega of G, we will say that the boundary of omega, or more precisely the set of sources, will be the set of vertices in your graph. And actually, since my graph will always be considered, when I mean a subgraph of G, I mean that it's, here it has the same vertices and a subset of its edges. So the set of sources is a set of vertices of omega, but therefore of G, so with odd degree. In omega. Okay? It's just a definition. So this is, it's called the set of sources. And we are going to use this terminology repeatedly, and you will see in the first lecture of next week, maybe one interpretation why we call it sources. Okay? So this morning we consider sourceless currents, sourceless graph, right? What we discussed, these loop models, this loop graph. this even subgraph. An even subgraph is just a sourceless graph, a graph for which the set of sources is empty. Okay. So this is one notation we need. Another notation which is going to be convenient for the rest of the lectures is for a subset, or maybe let's write it here. For a subset of V, sigma A would be by definition the product of the spins for vertices which are in A. Okay? Again, this is just a definition. And first proposition is the following. So fix G a finite graph and A included in V, then the sum for sigma of sigma A times the exponential of minus beta h of sigma. This thing, I can so if A is empty, this is just a partition function, okay? But if it's not empty, it's something different, and it's equal to 2 to the number of vertices in V, cosh of beta to the number of edges, times the sum over every graph omega with sources A. So that means that they have odd degree on vertices of A, even everywhere else, of hyperbolic tangent of beta to the number of edges in omega. Okay? So it looks quite like this morning. Remember this morning with the low temperature expansion, we had here we had the prefactor, which was e to the beta times the number of edges. And then we had the sum over omegas, but it was not omega on G, right? It was subgraph of the dual graph of G star. Here, my graphs are really on the original graph. So this is one big difference. And then we had the e to the minus 2 beta times the number of edges, which now is replaced by hyperbolic tangent of beta to the number of edges. Notice that before, when beta was very large, the e to the minus 2 beta was small. Now it's the opposite, is when beta is very small, hyperbolic tangent of beta is small. Hence the high temperature expansion, because it's going to be very useful when beta is large. In fact, it's going to be useful always, but originally, you could think that it's mostly useful when beta is small. So this was introduced actually a few years later, I think in 41 or 42, by van der Waerden. Okay, so let's prove that. So let's start when A is empty. So in this case, it's really the partition function, right? So again, we are going to do exactly like this morning. This thing, we are going to write it as the product over edges of e to the beta sigma x sigma y. It's basically what we did this morning. And then we said, okay, this thing is either e to the beta or e to the minus beta, depending on whether the edge is in your omega star or is not in your omega star. So here, we are going to use something slightly different. What we are going to use is that e to the beta sigma x sigma y, you can rewrite it, because sigma x sigma y is valued in plus minus 1, you can rewrite it, this term, as cosh of beta plus sigma x sigma y sinh of beta. right? If sigma x, sigma y is 1, you get e to the beta. If sigma x, sigma y is minus 1, you get e to the minus beta, which itself can be rewritten as cosh of beta times 1 plus sigma x, sigma y, hyperbolic tangent of beta. Up to now, everybody follows or sleeps, so that's fine. Okay? So when I rewrite this thing, first thing I see is that, well, good for me, the cosh to the power e appears naturally as a prefactor here. Right? So here is the trick now. We have a sum of product of a sum. So what I'm going to do is, in this product here, I have two terms. I have either 1 or I have sigma x, sigma y hyperbolic tangent. So I'm going to just expand in all the possible ways of choosing one of the two. Okay? And I'm just going to say, well, an edge is present in omega if I choose this second part. And otherwise, it's not present in omega. Okay? So here, this thing I can rewrite as a sum over every possible subgraph omega. At this stage, there is no constraint on the no constraint on the sources of, well, every single time I take omega, I have a sigma x, sigma y hyperbolic tangent of beta. So I have an hyperbolic tangent of beta to the number of edges in omega. That's perfect. That's what I want. And then I get a product over x of sigma x to what? I mean, sigma x appears how many times? Well, it appears exactly as many times as there is an edge xy. So it appears exactly degree of my graph omega times. So here I'm going to put degree of x in omega. Okay? Which may be, for simplicity, well, yeah, let's keep it like that. Good. So let's keep going. It's some very elementary manipulations, but you are going to see it's extremely powerful. So the cosh is still here, and now I'm just going to exchange the two sums. So I get a sum over omega. This term doesn't depend on omega, so I'm going to put it here. And here I get a sum over sigma of product for x in V of sigma x to the degree. Let's call it like that. I think it's... Okay? So what do I need to prove now? I almost have the relation I want here. Remember that A is empty. So the only thing I need to prove is that this term here is equal to 2 to the number of vertices times the indicator function that the boundary of omega is empty, right? If I prove that, I'm done. Good. Let's start by the simple thing. If indeed the graph is an even subgraph, so the degree is even at every vertex, then whatever the value of sigma x here, because it's plus or minus 1, if I put it to a power which is even, I get 1. So this sum is just the number of configuration. It's 2 to the number of vertices, period. Right? So the only thing I need to check is that this is also, that I get 0 if one of these degrees is odd. Okay? So if, then it's obvious. And if, so if, say, degree of x of omega is odd, then the observation is that there is a natural involution on the space of configurations, which consists in just flipping the spin at x. So from sigma, so from plus minus 1 to the v into plus minus 1 to the v, if to sigma I associate the configuration sigma x, which is simply defined as, so sigma x of y is equal to sigma y if y is not equal to x, and minus sigma x if y equal x. If I do that, this is clearly an involution, but at the same time, when I apply it to this quantity, what do I get? I get minus the quantity. The degree of omega of x in omega is odd. Therefore, here, when I apply to sigma to the involution, I get minus the quantity. So this quantity has to be 0. Right? So if you rewrite it very cleanly, this sum over sigma of product sigma x to the degree, or let's say sigma y of degree y of omega, is equal to the sum over sigma of product of sigma y x to the degree y of omega. This is just because it's a bijection, but this is just minus the sum of a sigma of product of sigma y to the degree y of omega. So this quantity is equal to its opposite, it's 0. Okay? So this was for A, which is empty. If I remove this condition, let's say I remove this condition. I take A arbitrary. So here I need to multiply by sigma A. I need here to multiply by sigma A. Here, well, I can multiply by sigma A here, or simply I can add here plus indicator function then x is in A. Right? This is exactly like sigma A here is going to add this thing to every vertex here. Right? Sigma x appears one more time if you are in A. But here it's still now, it's the degree plus indicator of x in A that needs to be odd. And same thing here, if it's equal to A, then you get something which is 0. So the fact that degree plus indicator must be even for every x is exactly telling you that the set of sources is A. Okay? Good. So this is van der Waarden high temperature expansion, and you are going to see it has a number of applications. And the first one is that the average of sigma A, which is a spin-spin correlation, you see how much spins are, you try to compute how much spins are correlated to each other. Well, this is this thing divided by the same thing with A equal empty set. So when I do the ratio of these quantities, this thing cancels for both things, and I end up with a sum for omega equal A of hyperbolic tangent of beta to the omega divided by the sum for omega equal empty set of hyperbolic tangent of beta to the omega. So you get a ratio. From now on, I will drop always omega included in G because it will always be the case. Okay? So you get a ratio of weighted sums over graphs. But one thing that is important to notice here is that these objects here and here are of very different kinds. Here it's sourceless, here it has sources. So it's not at all the same type of graphs on the top and bottom. So in particular, something which for a probabilist would be natural, which would be to try to just express that as the probability of something under a certain probability law. Here it's really unclear how you are going to do that. Because at this stage, these two objects are quite different. Okay. Let's see now what happens when you put plus boundary conditions. Imagine you try the same thing with plus boundary conditions. Okay. Well, you can try to run the same thing, except here you also have the e to the beta sigma x plus when xy is an edge which is incident to the boundary. Which is both having one endpoint in G and one endpoint outside of G. So the first thing that you observe is that here it's not really subgraph of G, it's subgraph of G plus edges which are emanating from vertices in G. Okay, so it's bigger graph. So they are not defined on the same graph. So here it's omega subgraph of set of edges, subset of edges of the set of xy with x in V. Y doesn't have to be in V. Second thing that you observe when you do that, so you have more vertices, you can expand like that. But here in the expansion, you also get vertices which are on the boundary. And these vertices on the boundary, sigma x, is equal to +1 for them. They have no choice. They are fixed, right? The vertices which are outside of my graph, their spins are fixed. So that means that in this argument here, well, here, it's not really going to be the fact that all the sources of my, all the vertices in my graph needs to be even degree. It's going to be only those that are in G. There is no constraint on vertices which are outside of G. So here, you should add intersection with V. Okay? So overall, you get the same result, except that here, you get intersected with V. So for instance, one example which is of interest to us is the case of sigma x plus lambda n, right? Or G, for what matters. And this is what now? It's the sum over omega for which the source is, so let's put G here, is empty of is x of hyperbolic tangent of beta to the omega divided by the sum for omega intersected with V equal empty set of hyperbolic tangent of beta to the omega. And notice again that here my graph omega is allowed to have edges like that. Okay? So in particular, an even subgraph here, a graph which has this constraint, is not necessarily made of loops. There are loops, okay? But there may be arcs going from boundary to boundary. Okay? And here, it's the same except that you have in addition a point x somewhere, and it needs to have a path going to the boundary. Okay? Notice one thing. Here I was careful not to ask anything about the parity of A. Right? I did the thing for any set A. But the formula that you obtain, at least when you don't have plus boundary condition, automatically gives you what? It automatically gives you that the thing is 0. So, remark, sigma A, so if I don't put plus boundary condition, if I put no boundary condition, is 0 if A is odd. And the reason for that is that whatever subgraph you take on a graph, the set of sources must be even. There is no choice for that. Okay? So if A is odd, this thing is empty. This sum is empty and you get 0. Okay? Of course, you are not expecting that to be true when you have plus boundary condition. But when you have plus boundary condition, there are graphs with sources only at one point with this constraint, because the other source is going to be somewhere on the boundary. Okay, so it also tells you actually that this is strictly positive, even if A is odd. Okay? So this is something I promised you this morning, that when you take plus boundary condition, you are really favoring pluses, and that shows it. In fact, here there is something non-trivial that we just proved, is that sigma A is always larger or equal to 0, in fact. Right? It's just the ratio of two positive quantities, I mean non-negative quantities. So last comment, and it's called the first Griffiths inequality. And it's saying that sigma A is always larger or equal to 0, whatever A. So it's very often 0, but it's always larger or equal to 0. Okay? Good. So this can look like something quite simple and quite elementary, but you are going to see it has actually an excellent application. This really is very useful. So let me give you this application. So it's related to the monotonicity properties of spin-spin correlation. So a spin-spin correlation is exactly this type of thing. So my goal is to use this type of things to deduce correlation inequality. So first thing I want you to observe, and maybe I should add it here, is that this is Griffiths inequality, but what actually we prove is stronger than that. We actually prove that both the numerator and the denominator are positive, in fact. For the denominator, it was completely clear. I mean, this was a sum of exponential of minus blah, blah. It was necessarily positive. But what we really prove is this, right? I mean, I want you to keep in mind this. Okay? So I'm going to try to use this in a clever way. So first proposition is called the second Griffiths inequality. And it says the following. It says that if you take two sets, A and B, included in V, then sigma A, sigma B is larger or equal to sigma A, sigma B. For people who know the FKG inequality or things like that, here it's a little bit the same thing. Spin-spin correlation are positively correlated. So maybe before let's prove it first and then see what we can do with it. Okay. So this is maybe the most, probably the most important correlation inequality for the Ising model. You are going to see in a minute why, but no, in a minute and in like 10 minutes and in 20 minutes and in 1 hour and in, we are going to use it everywhere, this thing, okay? And the proof is quite simple, in fact. So first thing you can observe here is that, so I want to prove that this minus this is positive, okay? If I multiply by the square of the of the partition function, if you want to earn time when you are writing, just drop the g and beta from it. Okay? So this thing is what? It's just a sum over pairs of configurations sigma and sigma prime, right? Of sigma A, sigma B minus sigma A, sigma prime B times exponential of, or let's say, exponential of minus beta or beta sum for every xy of sigma x, sigma y plus sigma prime x, sigma prime y. What did I do here? I just duplicated the system, if you want. I took two copies of the Ising model, and I said that sigma A, GB, sigma B, GB is sigma A, GB, sigma prime B, GB, because these are just two independent copies. And then I merge everybody together, and I end up with this. Okay? If it's not completely clear, you can just try to rewrite it yourself after the class. So now the observation is the following, is that I want to rewrite this as something positive, right? That's my goal. And I'm going to use this property. So I want to rewrite it as a sum of, well, quantities like that for some Ising model. So it's actually not so difficult to do. First thing you are going to do is you are going to define omega to be sigma, sigma prime. Okay? Let's define this random variable. This variable, and notice that this is also valued in plus minus 1. Right? And there, instead of summing on sigma and sigma prime, I'm going to sum on sigma and omega. It's just a change of variable in this double sum. So when I do it, I end up with a sum of omega and sigma, which I'm going to write like that. Here, I end up with what? I end up with sigma A, sigma B times sigma A, sigma B, WB, right? So it's 1 minus WB times sigma A, sigma B, this thing. Right? And then I get exponential of beta times sum over xy of sigma x, sigma y times, well, this is 1, and sigma prime x, sigma prime 1 is just wx, wy. So 1 plus wx, wy. Okay? So why is it good, this? Well, it's good because first thing, WB being always valued in plus minus 1, this is always larger or equal to 0. Okay? And second thing here, Wx times Wy is still valued at plus minus 1, so this thing here is either 0 or 2, right? Well, just think of this as the Hamiltonian of your Ising model at temperature 2 beta on the set, on the subgraph where the Wx, Wy is equal to 1. So define G So if you define G for every omega, define G omega to be the set of, to be the graph with vertex V and set of edges xy such that wx, wy is equal to 1. When you do that, beta times the sum of sigma x, sigma y, 1 plus wx, wy is just 2 beta times the sum for xy in g omega, or like neighbors in g omega, of sigma x, sigma y. So this big sum here is just the same quantity as here for temperature 2 beta. Okay, why not? On a subgraph, but here, this was true for any graph, so it's true in particular for the graph g omega. Therefore, this quantity here is also positive by 1 if 1 is this thing. So it looks like this is, not so difficult and so on, but it has this very nice implication. Why is it so nice? Because this has, for instance, a direct consequence, a corollary. If beta is smaller or equal to beta prime, then sigma A g beta prime is larger or equal to sigma A g beta. So the spin-spin correlations are increasing in the parameter beta. And in order to prove it, well, it's very simple. You just differentiate. If you differentiate sigma A g beta, what do you end up with? Well, I'll let you think about it, but it's the sum over every xy of sigma A, sigma x, sigma y, minus sigma A times sigma x, sigma y. This is just differentiating a ratio of two sums, so I trust you that you can do it. But what I just proved there is that this is larger or equal to 0. Okay? So beta gives sigma A g beta is increasing. Is non-decreasing. To me, the first time I saw the first Griffiths inequality, just the positivity of this spin-spin correlation, it didn't cross my mind that you could derive in like half a board that the spin-spin correlation are increasing. But there is this nice duplication trick in some sense, which allows you to do the job. Okay, so this second Griffiths is a direct consequence of the first one, and it's very, very important thing. Okay, another corollary, while we are at it, is that if you take two graphs, G included in H, then sigma A in G beta is smaller or in H beta is larger or equal to sigma A in G beta. So not only are the correlations increasing in beta, but they are also increasing in G. And here, I must say I'm going to cheat a little bit. And just say, okay, in all what I did, in fact, if you think about it, I didn't really need here I could have had any jxy here. It would have worked exactly the same. Okay? So another way of putting it is that you could have that the beta is depending on the edge. Okay? So how do you obtain a bigger graph from a graph G? So imagine you have a graph G, a graph H. How can I interpret these two things in the same graph? Well, sigma A H beta is just spin-spin correlations in my graph H. Good. Sigma A G beta, well, it's only with these edges, but what you can say is that it's in fact on the whole graph, except that all the edges which are in H but not in G, their beta is 0. Right? If beta is 0, it's not going to interact at all with your spin-spin correlations. So if you interpret it like that, sigma A GB, G beta, is just sigma A H, and I'm going to put a J and a B bar, where B bar where beta bar is equal of xy is equal, beta bar is a function of x and y. With beta bar of xy equal beta if xy is an edge in G and 0 otherwise. Since beta bar is smaller or equal to beta, where here you allow me this kind of small lack of, beta here is identified with a function of edges which is constant equal to beta. Since beta bar is equal to beta and you are increasing in each one of the beta xy, you end up automatically with the inequality you want. Okay? So here, try it. It's a good way of checking that you understood what happened. Try to do it with jxy positive, everything I'm doing this afternoon. And you are going to see everything works fine. If you manage to redo it, good. If you don't manage to redo it, it means that you didn't understand what happens here. So why did I mention this corollary? Because for any set A, if you take and second thing you can do is try to do it with plus boundary condition and check that it also works. If I look at this quantity, sigma A plus lambda n beta, and I looked at the sequence of these quantities for n belonging to the integers. When you look at that, well, the sequence is increasing. It's bounded by 1, so it converges to something, right? So this thing converges to something which you can call, I don't know, f of A. Now, this is true for any set A, and you can also check that this f of A, here you have consistency relations for these guys. For instance, if you look at sigma xy and sigma x, sigma y, they have to be related. So since you have consistency relation there, you have also consistency relation there. And what you can check easily is that there exists a unique measure on ZD for which, so there exists unique measure on ZD for which f of A is equal to sigma A measure. Okay? Well, this measure, you call it the plus boundary condition Ising measure. Okay? So this measure, you call it the plus infinite volume measure.
Measure on not on ZB, but on minus 1, 1 to 2.
On minus 1, 1 to 2, yes. Thank you. Yeah. And then once you have this measure, the fact that the sigma A converge, because they generate the sigma algebra, it implies automatically that any random variable of finitely many spins converges. So you get your free energy, your weak convergence, automatically. And that just justifies the fact that this subsequential limit that I was taking this morning wasn't necessary. You could just take the limit. The sequence converges. Okay? So the sequence converges because of the monotonicity in the graph of the spin-spin correlations. Okay. Where am I? Good. Okay, so let me give you a second big application. So this is really very, very important. It's going to be extremely useful for us. There is going to be another thing which maybe is less emphasized in usual classes on the Ising model, but which I think is extremely important, is another correlation inequality called the Simon-Lieb inequality. And I want to put it here because I really want you to remember this one. For people who like Bernoulli percolation, it is really what is going to replace the decay inequality. So in Bernoulli percolation, we have usually the FKG inequality and the decay inequalities that pop up in many places. Well, what will replace the FKG inequality will be the Griffiths inequality, usually, and second Griffiths. And what will replace the decay will be the Simon-Lieb inequality. So it's a very, very important inequality. And it says the following. So pick a point X and a set S and assume that X doesn't belong to S, but 0 belongs to S. So you take a set S of vertices, you have 0 in it, and you have X outside of it. Okay? And let's define the boundary of S. So maybe, yeah, okay. The boundary of S is the set of vertices in S so that there exists a Y which is, there exists a Z which is not in S and such that YZ is an edge of ZD. Okay, so it's the set of vertices that have one neighbor at least outside of my set S. The standard notion of boundary in a graph. Well, the Simon-Lieb inequality says the following. It says that you can bound sigma 0, sigma x by the sum for every y on the boundary of S of sigma 0, sigma y S beta, sigma y, sigma x, g beta. So let me comment a little bit on this before I prove it. So first remark is that, I mean, it's a historical remark. Why is it called the Simon-Lieb inequality and not the Lieb-Simon inequality like alphabetical order should suggest? First, because Simon and Lieb are more physicists. I mean, they are in between math and physics, and that in physics sometimes it's not in the order. But more importantly is because Simon proved, in fact, an inequality which is slightly weaker. So what he proved is the following. Let me drop the beta. So he proved it with G here. That's the subtlety. So it can appear like not very different from the other one. I mean, why should one care so much about having G or S? But you are going to see in the applications, in fact, you basically always use S instead of G. It's really like a gain which is enormous in some sense. And notice that it's really a gain since we have monotonicity, right? This guy is smaller or equal to the correlation with G, since S is smaller than G. So it's Lieb who proved the better version. Hence the Simon-Lieb. But really the first person to notice that such an inequality was useful was Simon. So that's the first remark. The second remark, and it's not going to speak too much to people who didn't do Bernoulli percolation in their life, but notice that for Bernoulli percolation, you have an inequality, which is the following. If you look at the probability that 0 is connected to x in Bernoulli percolation, it's smaller or equal to the probability, to the sum over y on the boundary of S of probability of 0 connected to y times probability of y connected to x. Yes? It's the color. So here it is a G, right? So it's a full graph. And here it's really the set S in question, which is much smaller. Yeah.
And there you have 0 connected to y within S, I guess.
Exactly. Here you mean. Yes, that's what I want to say. Yeah. Exactly. Yeah. So how do you prove that just like in 3 words for people who know Bernoulli percolation? For others, it's... So what you say is that for 0 to be connected to x, 0 needs to be connected to some vertex on the boundary of your graph, within some vertex on the boundary of S, within S, there must be a path to the boundary. And then this point needs to be connected to the boundary. Okay? Now, if you think about it, you can improve that and say that there is a point on the boundary which is connected to 0 in S, such that it is also connected to x, but not using the same path. So you see, if you have S, you have 0. Of course, you can say there is a point on the boundary which is connected in S and connected to the boundary, to x, But if you choose this point poorly, it may be connected using necessarily bonds that were already used to connect 0 to this point, if you do it naively. But what you can observe is that there is always actually a point which is not like that. It is connected in S to 0, and it is connected to the boundary, maybe reusing, by the way, edges in S, but not reusing the path from 0 to x, from 0 to y. Okay? And then there is this inequality in Bernoulli percolation, which is called the decay inequality, that tells you that if you have 2 events like that occurring, but they occur using different set of edges, then the probability of the intersection is smaller than the product of the probabilities. Some kind of reverse negative correlation between events that use different set of edges. And therefore, that's how you end up with this thing. The sum over y is for the sum over the possible points, and then the product, instead of having just comma, the intersection, comes from this decay inequality. It's something which is extremely wrong for dependent type percolation models. but which holds for Bernoulli percolation. Well, this is really the analog in some sense. I mean, this is really the analog, and that's one of the reasons why the theory of Bernoulli percolation progressed a lot in the second half of the 20th century, and the one of Ising as well. While many of the theorems that you could prove for these two models remain untouched for more dependent percolation model, for instance. Because they didn't have decay, and you don't have Simon-Lieb, basically. So really think of one of the magical things happening for Ising is the occurrence of this Simon-Lieb inequality, which I'm now going to prove, hopefully. Okay. So we are going to try to follow a little bit the intuition from Bernoulli percolation, the intuition of path. So what we are going to do first is to observe that, so this thing, right, I know, let's rewrite it. I know that this is written, let's drop the beta. This is written as a sum for any omega which has sources 0 and x of, let's put t instead of hyperbolic tangent of beta. Okay, it's going to be shorter, so t of omega divided by the sum of t to the omega, right? This is the high temperature expansion. So here, notice that if I take a graph which has odd degree at 0 and x, and only at these 2 points, when first thing, 0 and x are necessarily connected in this graph. It's a necessity. And a way of understanding that, which is going to be useful for us, is that you can start some kind of peeling process of your graph by doing the following. You start a small robot here. This doesn't look like a robot, but anyway, a small man. Sex equality, a small woman. That's better. So what it does is the following, what she does. Maybe I'm going to regret what I just did. So what she does is the following. There is a certain order on the different edges of my graph. I just order them to start with by lexicographical order. Okay? And what she does is that she checks the first edge, the smallest edge incident to it, to the vertex where she is. And she just checks whether this edge is in my graph or not. Okay? If it's not, she just says, okay, this is checked. I'm never going to visit this vertex again. And I check the second smallest one incident to me to check whether it's there or not. Let's say that we are lucky, it's there. If it's there, she just walked to the other endpoint and close this thing. Says, okay, now it's discovered. And she proceeds from there, checking the smallest edge incident and so on and so on. Okay? She does that until she cannot do it anymore in the sense that she's at a place where everything is closed around it. There is no edge incident anymore. Where can this thing be? Well, at the beginning, I have an odd degree, so I'm certain to be able to start because I must have a vertex somewhere. So I start, I arrive here, and now I kind of burn this edge, right? If the degree here was even, after I walk here and I kind of burn this edge, now the degree is odd necessarily. So I will be able to keep going. I do it again. Every single time I arrive somewhere, I burn one edge, and every time I leave from it, I burn the second edge. So what is the only place where I can stop eventually? Well, it's at the place where when I arrive, I burn an edge, and now I have an even degree, which maybe means that there is nobody anymore. Okay? So the only place where she can stop is the end thing. So let's call the path that she did, which is a deterministic path of a deterministic subgraph of omega. Let's call it gamma of omega. Okay? Okay? So there is a deterministic way of peeling off a path from 0 to x. So in particular, this path is a connection from 0 to x. But we are going to go much farther with this notion. Because what we can do here is we can try to re-express that depending on the value of gamma of omega. So what can we do? We can say it's the sum over every path gamma from 0 to x of what? T to the gamma times, well, times t, so maybe sum of omega such that gamma of omega is equal to small gamma of t to the omega divided by the sum of a sourceless omega of t to the omega. Right? I can just resum like that. But notice that here, this, I can rewrite it as t to the gamma times the same ratio. So sum for every omega such that gamma of omega is equal to gamma of t to the omega minus gamma this time divided by sum of the omega of t to the omega. But this we kind of already did before. If I remove a path from 0 to x, which has sources, a path from 0 to x, to a graph which has sources 0 and x, what remains is just a sourceless path, right? A sourceless graph. So here I have a sourceless graph, and here I have a sum of a sourceless graph as well. So there is a small subtlety, which is this sum here is on which graph? So I'm taking sourceless graph of which graph? The first intuition is to say, well, I'm taking sourceless graph on the graph which is made of the remaining edges, right? All the edges remaining, right? That's the most natural thing. But it's not quite true. Because, for instance, this edge here, which was anterior to this one, and therefore was checked, well, this edge is necessarily 0, is necessarily absent. So here, careful, but this is only on graph, so this is equal to the sum of a sourceless graph on what I will call G minus gamma bar of t to the omega, divided still by the sum for sourceless one, and this time I'm going to put on G to put the thing, where here gamma bar is a set of edges that must be discovered to guarantee that gamma of omega is equal to gamma. And notice that it's always the same set of edges, whatever the omega. So it's all the edges of gamma plus all the edges which are anterior in the lexicographical order, which must be closed. Okay? Okay, so now let's just take the intuition here. This is a set on every path gamma from 0 to x, where this path needs to exit at some point S. So let's decompose. So let's decompose gamma into gamma 1 and gamma 2. So, okay, maybe a drawing is going to be better. So you have 0, and just gamma 1 is going to be the whole path. So notice that the path can be self-touching, or even, it can visit a vertex several times. It's just it cannot visit the same edge. It's an edge-avoiding path. Up to the first exit, and then gamma 2 is the remaining of the path up to X.
But gamma 2 can come back now and
Yeah, it can come back. It can come back. This is a bad.
No, it can intersect gamma 1.
It can intersect the edges of gamma 1, indeed.
The sites.
The site. Yeah. But gamma 2 is a path in G minus gamma 1 bar. That is still true.
Gamma 2 is in G minus gamma 1 bar.
Yeah. Okay? It's just an edge. A priori, it could.
But it still can visit gamma 1.
I agree. Okay. So let's decompose in gamma 1 and then gamma 2. So in gamma 1, I get t to the gamma 1, and then I have in gamma 1, gamma 2, and then I have this sum sourceless on G minus gamma 1, gamma bar, divided by sum of the sourceless on G. Okay, I'm dropping a little bit, simplifying a little bit the notation, but I think that Okay, so let's sum over gamma 1. And by the way, here the decomposition is such that gamma 1, and let's maybe sum over y on the boundary of S, with gamma 1 from 0 to y in S, and gamma 2 from y to x in G minus gamma 1 bar. Okay? So let's decompose and just keep gamma 1. So it's a sum over gamma 1. Okay, T of the gamma 1. And what I would like to do is to see, so now I have a sum over gamma 2 from y to x, gamma 2 included in G minus gamma 1 bar, T to the gamma 2. Here I would like to see the spin-spin correlation appearing. And up to now, what I have is Z. I have the sum of a sourceless current in G minus gamma 1 union gamma 2 bar of T to the omega. So I don't, you see here, and here I have, say, over sum of sourceless on G of T to the omega. Here I want to make the following quantity appear. What am I missing to make this appear? Well, I'm just missing, this is almost that, right? When you look at a decomposition like that, it's almost that, except that you need to divide by this thing, right? If I divide by this whole thing there is equal to this. Simply, it's just what I wrote there, right? Dun, 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 dun. Okay. No, huh? Who understood? Okay, I was hoping that somebody will darely, put his hand up that I can ask him to come. Too bad. So here, that was sigma 0, sigma x, g, right? It's a sum of a path in your graph, g, t to the gamma, and then the sum of the remaining guys divided by sum over all the sourceless guys to start with. So here, think of, I'm not in G, I'm in G minus gamma 1 bar, okay? I'm summing over every pass from y to x in this G minus gamma 1 bar. I have a t to the gamma, t to the length of this pass, sum of the t to the omega for sourceless guy in the complement, right? This you can also write it as G minus gamma 1 bar minus gamma 2 bar, right? It's the same thing. So the only thing I'm missing to get this guy is just this term. This term for G minus gamma 1 bar, not for G. So this was on G. So here I just divide by the thing on G minus gamma 1 bar, and I multiply, because this is not there, I multiply, that's maybe what I forgot, by G minus gamma 1 bar. I asked just a little bit too early if people understand. Okay, so I multiply and I divide by the same term, just that now this thing is this quantity. But notice the good thing about this quantity is that, well, I have my monotonicity in the graph. So this is always smaller or equal to sigma y, sigma x in G. So already what I get is that this is smaller or equal to this, and there is a sum of a y. So it's a sum of a y on the boundary of sigma y, sigma x, g. This is perfect, I wanted it. And then remains the sum for gamma 1 from 0 to x, to y, sorry, gamma 1 in S, of t to the gamma 1 times the ratio of the two sum. This is not a very simple inequality to get, but it's going to be very useful. So at some point you have to suffer to be pretty. Okay? Actually, this is a very wrong statement, but here we are going to have. Okay, this term now. Let's be Simon strong. So if we just want to prove Simon inequality, do we actually have to do a lot of things? Well, no. This is a sum of a path from 0 to y in G. Well, I'm asking that they are in S, but if I forget the constraint on in S, I'm just summing on every path from 0 to y of exactly the term I want to end up with the spin-spin correlations. So if I forget the in S, so if we forget the constraint gamma 1 included in S, then we automatically get and here I'm getting sigma 0, sigma x, g. Right? This will just be a sigma 0, sigma y. So Griffiths inequality is just, if you want, a decomposition of your kind of backbone, like this path that I wrote for the path that I wrote in omega, this gamma of omega, is just a decomposition with respect to the first exit point. Okay? So what I need now to do is to be explaining why, if I restrict my path in S sorry, if I restrict my path in S, then I can get sigma 0, sigma y, S. One thing that is clear, notice that if I can prove that this ratio is smaller or equal to the same ratio, but when I replace the G by S, if I can replace it by S, and I get this inequality, then I would be done, right? Because here I replace it by the graph in S. I'm summing over every pass from 0 to y in S, so for every pass in my new graph, which is given by S, and I would get exactly what I want, right? So the only thing I need to prove is that here, when I look at that, if I replace G by S here, I increase the ratio. Okay?
But it's important that gamma bar is subset of S. So you can't replace gamma.
Yeah, if I lose here the gamma 1 in S,
then it's not true anymore.
then I'm doomed because, yeah, it's not true anymore. And even if it would be true, since I'm using anyway paths which are not in S, I would, but yeah. Okay. So here there are two ways of going, a wrong one and a right one. So let's start by the wrong one. When you look at this quantity, can you re-express it in terms of the Hamiltonian of the Ising model as, I don't know, the average of something? The answer is yes. This thing well, this is up to 2 to the number of vertices, cosh of beta to the number of edges. Well, and if you put minuses, this is just the sum over sigma of exponential of minus beta edge of f g of sigma, right? Here you can also, this is just the high temperature expansion. Here you can run exactly the same argument in G minus gamma 1. So it's going to be 2 to the minus. Let's assume that the set of vertices is the same always. You can always assume it's the same anyway. Cosh of beta, this time I'm going to have my E minus gamma 1 bar. I remove the vertices in gamma 1 bar of the sum of a sigma of exponential of minus beta times the Hamiltonian in G minus gamma 1 bar. Right? Okay. But this Hamiltonian can be expressed in terms of this Hamiltonian. It's just the Hamiltonian plus the sum over the pairs that I'm missing. So this whole thing here, when you rewrite it, you can just up to something which is 1 over cosh, I mean maybe cosh of beta to the gamma 1 bar. It's just the expectation in G beta of exponential of minus beta times h gamma 1 bar of sigma. And maybe there is a plus, sorry. There's a plus. Okay? Okay. You can do the same here, right? You can do the same, except that what you are going to end up with is going to be with a S here. Okay? So this inequality is saying what? It's saying that the exponential of beta times, I mean, if you want, this is just the product over xy in gamma 1 bar of e to the minus beta sigma x sigma y, right? It's saying that the average of this quantity is decreasing in the graph, which is not so surprising if you think about it, because here it seems to be like kind of a decreasing function of sigma x, sigma y. It's e to the minus beta blah. Problem is that it's a product of this thing, so this whole thing is not a decreasing function of the spins or anything like that, so you cannot use any correlation in she loves me. Oh, it loves me. So you cannot use a correlation inequality to prove that it's decreasing in the graph at this stage. So the trick, and this is actually a trick that is good to remember, is that instead of writing this thing like that, here, write this guy as edge of G minus gamma 1 bar plus edge of gamma 1 bar. So write this whole thing as something like cosh of gamma 1 bar, cosh of beta to the gamma 1 bar. But here write it as 1 over the average in G minus gamma 1 bar of E to the minus beta edge of gamma 1 bar of sigma. It's exactly the same. You can write it that way. You just consider that the graph at the beginning doesn't have the edges in gamma 1 bar, and you just look at something like that. But this here is exponential. It's the product for xy in gamma 1 bar of exponential, or I mean you can write it like that, it's exponential of beta sum over gamma 1 bar of sigma x, sigma y. So now this doesn't have the minus sign anymore.
But I'm confused. So,
yeah.
So you take average over an Ising configuration in G minus gamma 1 bar. On the other hand, your H depends on the spins in gamma 1 bar.
Yeah, but you see here, I was careful to say, to protect myself. Maybe I didn't say it in the same. Okay. But the graph, the original graph still has all the vertices in it. Yeah. It's only the edges that are removed, but it's not because you don't have an edge between two vertices that you cannot look at the product of sigma x, sigma y.
So the second formula tells you exactly what to look at.
Yeah. Exactly. Exactly. So, yeah, you mean this thing? Okay, now I understand.
The second tells you what
okay, yeah, okay. Yes. So this is perfect because this gives an excuse for people because they can all say, now I understand. Good. Yes. I claim now that what we need to prove is that this is increasing in the graph. If you increase the graph, it's bigger. But notice that this is just a big sum. If you expand your e to the beta blah blah, it's a huge sum on graph A with even cardinality, some coefficient Ca, which is always going to be positive, of sigma A, and it depends on beta of course, on sigma and on gamma 1 of sigma A in G minus gamma 1 bar. Okay? Just expand completely. You have because you are expanding e to something, you have only positive terms, and then you expand this thing to the power k, you always get positive terms. So you end up on a sum of positive terms times your correlations. But your correlations are increasing in the graph, therefore the whole thing is increasing in the graph. Okay? So that means that this, which is roughly up to a common constant 1 over the quantity, has to be smaller than this thing. It is.
Lieb's original proof?
No. If you don't like this proof, go read Lieb proof and apologize to me afterwards. No, I mean, the original proof is actually cleverer, but I mean less transparent in some sense. This is a transparent proof. Now, to me, it's transparent because it's really following exactly the path of percolation. Then, of course, you are manipulating big sums, and when you are manipulating big sums, you think, why this guy is like writing all these sums? I'm bored, and then you start to be less careful, and you drop. But if you read again the proof, it's really like line by line. It's a sequence of simple observations. Okay. So exercise for tomorrow, and I will do it after. I mean, I will start by that. Define the susceptibility of your graph to be the sum of sigma 0, sigma x. Think of when you are on the infinite graph. Okay? Think of, and put a plus if you want. The Simon-Lieb is true with plus as well. Don't worry with that. So take this quantity, okay? Assume it's finite. Okay, so assume chi of beta smaller than infinity, and prove that there exists a constant c such that sigma 0, sigma x, beta plus is smaller than exponential of minus c times x, distance to x. So prove that if the expectation, the sum of the correlations is finite, in fact you have exponential decay automatically of the correlation. And this is going to be extremely useful for us because at some point we are going to want to prove exponential decay, and we are going to use this observation. Second thing you try to do with that, so normally if you manage to do that, you are going to observe that you only need the Simon inequality to do it. So you are going to damn me for not stopping on this board. But then try to do the second step, which is try to prove that the susceptibility at criticality is infinite. So second step in the exercise, chi of beta c equal plus infinity. So this is actually telling you that at criticality, you don't have exponential decay. You actually don't have such a rapid decay. The thing is necessarily non-summable. And this is a very, very important observation. And that, you need Simon-Lieb to do that. So I will do it anyway tomorrow, but I think it's a good exercise. And for people who did percolation, you already saw, I guess, things which look the same. Okay, thank you very much.